All right, for the inverse sine and cosine, inverse secant, inverse cosecant, inverse tangent, and inverse cotangent functions, their derivatives will rely on some tricks that we might want to use. So, what we're going to do is we're going to we're going to start with the arcsin function. And so, we're going to take this definition that y is equal to the arcsine of u. And this is going to let us have du dx. In fact, I think just for notational sense now, I'll make this x, and we can make a little more out of it. Now, the arc function has a domain that's trapped between -1 and 1. And it has a range then of -pi/2 to pi/2. Now we're going to notice that the derivatives, though, if we look at our sine function in its own right, does this. And at -pi/2 and pi/2, we get our horizontal lines. So the derivative is not going to be able to exist here because of the zero problem that we had when we defined the inverse function. But what we're going to be doing is we're going to be looking at this part of the sine function because it doesn't repeat. So it can have a proper inverse. And to talk about that inverse, let me switch colors here. We're going to say that we're going to make x is equal to the sine of y. Right? We're saying this undoes the sine function. So if I were to drop sine of y into here, if sine of y drops into here, then it undoes the arcsine undoes the sine function. We're left with y, which makes this true. So we're looking at this being kind of our definition that we have. So what we're going to do then is we're going to do a little variable waving here and say that if we want to find the derivative of arcsine of x, then we're going to make our f of x equals sine of x. And our inverse will equal arcsine of x. So that's our starting point. Then what we'll do is we'll use our inverse theorem. So let me get parentheses in place here. The inverse function, its derivative, is going to be 1 over the original function evaluated at the inverse at x. 1 over the derivative. Right, so we'll use the derivative. So let's first set our, using this definition here, we'll say the function of y is equal to sine of y. The derivative of y is cosine of y then. And now we want to actually play a game with this. We want to play a game in this where we're going to have this relationship appear back to us. That we're going to want to see the sine function come back. And so what the book hints at is using the Pythagorean theorem. And so in our Pythagorean theorem, cosine squared of y plus sine squared of y equals 1. So if I want to get cosine on one side, cosine squared of y equals 1 minus sine squared of y. Take the square root of both sides, and I get 1 minus sine squared of y. But since we're evaluating this at x, then this will become 1 over cosine y evaluated at x or evaluated at arcsin of x. All right, so we're going to get the cosine evaluated at the arcsin. And then we're going to use this definition of cosine. So this becomes 1 over 1 minus sine squared of the arcsin of x. And we'll transfer this over just a little bit here. And then we look at this, and arcsin of x in the domain of x, or sine arcsin of x, I should say. So let's kind of sine arcsin of x squared is what this inner notation is telling us here. But the sine of an arcsine undoes this, right? An inverse, so that leaves x all by its lonesome. And this becomes 1 minus x squared. And so we can say that the derivative of the arcsine of x is equal to 1 minus 1. Oh, there we go. 1 minus x squared, all under the square root. But this will only work when x is trapped between -1 and 1, not including, and we'll sometimes write this as the absolute value is less than 1. And the chain rule then lets us say, and let me change colors here, that d dx of arcsine of u, if u is a function differentiable in x, then this is 1 minus u squared, 1 over 1 minus u squared times du dx. And so the chain rule applies to that also. Let's look at a chain rule application. Since the book looks at it now, we'll continue with the book's version of it here. And so we'll ask ourselves, what's the derivative of arcsine of x squared? So since we have a u equals x squared and du dx equals 2x, then this will be 1 over 1 minus u squared (2x). And u squared is 1, we'll do this whole thing, x to the 4th times 2x. And if we trim it all up, we get 2x over 1 minus x to the fourth. So we're able to get an arcsin function and the derivative of an arcsin function. I'm going to stop this here, and then I will add the derivative of the arctangent. I'll stop that, and I'll add the derivative of the arcsecant.